Hi everyone, my name is Sarah Daly. Thanks for coming to my presentation for our final project. So my ensemble is a model to aid in predicting chronic heart failure after myocardial infarction, which is just another word for a heart attack. So I'll go into the summary. The goal, again, is just a tool to assess for the risk of chronic heart failure after hospitalization for a heart attack. It's not intended to be a diagnostic tool. The process is data collection and then shaping heterogeneous ensemble, which consists of those four submodels. I will, of course, talk about the heterogeneous ensemble last. And then we'll go into a discussion, an evaluation and comparison discussion, and a quick discussion about potential deployment in the real world. So the data collection phase, I of course did not collect the data myself. This came from the UC Irvine Machine Learning Repository, which we've used a lot in our homeworks. This specific data set came from a study called Trajectories, Bifurcations, and Pseudotime in Large Clinical Data Sets Applications to Myocardial Infarction and Diabetes Data. So this study, again, is more based for data science as opposed to like medical research. There were 1,700 patients worth of data and 111 features and measurements during hospitalization. Some of them are right at admission and some are a couple days into the hospital stay. There are 99 categorical features and 12 continuous features. And again, the target I chose is chronic heart failure just because this is something that impacts a lot of people and it's pretty broad, so I thought it would be applicable and interesting to talk about. So we'll start with data shaping. I started by finding the missing values in the data set, and I will go into R just to show quickly how I did that. So first I made a list of the percentage of missing values by feature. So this one has quite a few and will be eliminated, of course. And then I created two functions to impute those missing values based on mode for the categorical features because those are not linearly related, so it wouldn't make sense to do median or mean or something. And median for the continuous features because those are related linearly and using the median makes sense. And both of those methods will just preserve the distribution of the data and the median in particular just to eliminate any outliers from weighing too heavily. I also tied the imputation of missing values to sex and the target of chronic heart failure just because a man or a woman might have a really different metric for various features when they're experiencing a heart attack, and I didn't want that to skew the results. And also, I didn't want the nature of the class imbalance of the target feature. There are more negative cases than positive cases, so I didn't want that to overwhelm the imputed values either. So we'll talk about outliers. I did this kind of on an independent review basis, so I used the z-score, but you can tell for an example like this, this is a measurement of, let's go to a really dramatic one. See this here. This is a measurement of erythrocyte sedimentation rate. So there are features that I did leave in the outliers for, things like sodium, potassium, which could have a really extreme value for someone having a heart attack. But for something like this, I did some research and found that this is more related to an infection. So this person might be experiencing some comorbidity that's not related to a heart attack. So I went in and removed those on a case-by-case basis. And I did create a function to do that. So I'm thinking of the imputation function is based on the percentage of missing values, 25%. If there are more than 25% missing values, the feature is removed. But for the outliers, I went in and removed those just after a review of each feature to see, like, after doing some research and saying, is this medically relevant and possible, or is this just like completely unrelated and needs to be removed? So for encoding, I encoded the categorical features using the one-not method just because the levels within those features are not ordinally related, so that would preserve that. I performed a collinearity analysis to help in feature removal. This is of course more relevant to the continuous features, but I did also perform it on the one-hot encoded features, and we can see a result of that. There were some correlations that I removed on that basis. And what aided me in removing these features is the random forest model's variable importance plots. We can go into that next. So the random forest model really helpfully, you can plot this variable importance plot based on the Gini index, which is, it kind of decides which features are the most useful at at decreasing the variance in the data. So which are the most useful features to perform a split at, because the data after that split is less chaotic than the data before it. And so I use that in coordination with the multicollinear analysis to remove some features. Okay, go into the random forest model. So I did two. I built the first one just with the basic model. The second one I used the Carré data splitting and train control functions. And I will show that quickly in R. So these are kind of some of the tuning functions that I used in the second model. I used repeated cross-validation, and I tested these number of different splits. So like taking 5 features, taking 10 features and 15 features, and seeing which two to split at. And I also played around with just a few different things, the different size of the training set, and things like that. So moving on to, I'll talk about evaluation at the end. These are the metrics down here, but I don't want to suck up too much time on each slide for that, so I'll go over that all at the end. Moving on to the logistic regression ensemble, I started using just the logistic regression function in R, and I boosted that a bit with the step function, which removes features that are not statistically, that they're not aiding in the predictive power of the model based on the AIC value. I ensembled that, and I also introduced let's go to it, a positive class weighting, just because in healthcare data you really don't want to have false negatives, because then you've got someone who might have the disease and you've missed them. So I chose a weight of 0.3 to say, usually it would be 0.5 is one, and then the other, if you get above that, it's negative. And I said, let's decrease that so that even if it's not if it's not super confident, it might still grab that positive, because I figured that a false positive is worse than a false negative for this use case. And again, there are the evaluation metrics I'll go over at the end. Next, I did a support vector machine ensemble, and for all of these, I also used bagging for the linear regression and the support vector machine. I used bagging. Some of the tuning features that were really cool here were the kernel selection. So go to that. So the kernel selection feature, it allows you to find the best hyperplane through the positive and negative cases that does the best job at maximizing the difference between the way you're classifying that. So getting them to be as separate as possible in the kind of cleverest way, I guess you could say. And I landed on the ANOVA dot technique. I also applied this weighting technique to try to make sure that there were fewer false negatives, as you really don't want that, again, in healthcare. And that's what I mean when I say positive class biasing. So next, the adaptive boosting. So again, I performed this before and after making the final heterogeneous model, just because I wanted to see if boosting, this technique wherein a model kind of successively builds on itself, on the weakness, it analyzes its weaknesses and then performs from there. I wanted to see how that could impact the final model. I attempted to do this with the cross-validation method, but I wasn't able to get it to build into the heterogeneous ensemble, so I did stick with the basic AdaBoost function from the AdaBag package, and there is some overfitting risk involved there, but that's why I kept both alternatives. So the final myocardial infarction heterogeneous ensemble, again, I'll just go into R because I think that's a better way to show how I built it. So, okay, we have here, the first time I did it, I combined the random forest linear regression and the support vector machine without the boosted model. And I again applied this positive class biasing and made predictions, calculated the metrics based on that. And then I performed it again, including the including the boosted model. ran everything again, and compared the evaluation metrics from there. So here's just a kind of comparison of those different metrics. So the ones I focused on are sensitivity, which is also called recall, and that focuses on the out of all the positive cases that are in the data set, how many did the model actually capture? And then the F1 also kind of, it takes sensitivity and adds precision onto it. Accuracy, of course, handles, out of all the cases possible, how many did it accurately label true positive or true negative? And then the kappa kind of compares the accuracy to like a random chance or guessing. So a poor kappa would be 0, and a good one would be, the best one would be 1. And that's kind of saying like, how likely is it that you got this based on random chance? And so for each of these models, we can see the random forest, the sensitivity, not great. There's a lot of false negatives in there. It's getting a little bit better with logistic regression and sport vector machine. And finally, in the boosted ensemble, it was good. The F1 score, again, it's kind of just improving all the way up to the final ensemble. Accuracy goes up and down a little bit, but I think accuracy isn't, the most useful metric for this purpose. I just kept it in here because it's easily understandable. The kappa is what's most interesting. It did seem to increase a lot with the boosted model. It also, the model before boosting was also, it was about 0.71. So that's kind of saying that it's unlikely that you would get these classifications just if you were guessing randomly, which is good. And let's talk about some of the challenges, improvements, kind of flaws, and then final use cases here. So some of the challenges that I was thinking about when I was building this is, again, that false negative problem. So I did strive to build in positive class weighting just to make sure that there were, to bias the model against popping out false negatives, as this would really be bad. Another thing that I was struggling with was the concept of the voting method. So I thought maybe if I did this again, I would try to focus on probabilities as opposed to classifications, and say, that might allow a better tuning ability, and it wouldn't just be, an average of 4 values, which is a little bit basic. Some improvements I would make for sure are having more real observations with better target class balancing. So what I mean by real observations is I could have I didn't touch much on the topic of class imbalance just for time's sake. I don't want to suck up all of your time, but we want to make sure that the positive and negative classes are somewhat equally balanced. But if I were to use a technique like SMOTE to introduce a bunch of synthetic data based on undersampling or oversampling, I would have probably gotten a lot of lines of data that had combinations of features that were not medically realistic, and that might have just made the model weaker overall. So I didn't want to do that. But in the future, if I had more data, I might try to remove some of the negative cases and rerun the model on that. I also would have performed a better multiple correspondence analysis and more feature engineering. So I did play around with multiple correspondence analysis, which is sort of the principal component analysis for categorical features. I did play around with that a bit using the facto minor package, but the dimensions that I was getting, I made a scree plot, and the dimensions that I was getting from that were really not they were not decreasing the variability enough for me to use them in the final analysis. I just didn't feel like it was going to add much to the model, and I was just in kind of a time crunch, didn't really have time to perfect it and then use those dimensions as the features for the model, which I would have liked to do. I would have also liked to do some kind of stacking. I looked into this a little bit. Stacking, of course, using the predictions of the models as the features as opposed to ensembling the models that way. I think that's something I could definitely do in the future. And just some use cases. Again, this is mostly supposed to be a risk assessment aid. It is not supposed to be a diagnostic tool, so it could be something that a less experienced clinician could use just to make sure they're not missing anything. It could even just be like a checklist item on when someone's leaving the hospital and their team is going through all the potential risk factors that they want to look at going forward, and they say, okay, chronic heart failure is something that you're more predisposed to, or you're maybe more likely to get than someone else, so let's consider this carefully in your treatment plan going forward. But again, really would not be a diagnostic tool, especially just because of those false negatives, and the sensitivity metrics we were seeing were not ideal for that case. But yeah, there's a lot more I could say about this, but I'm at about 15 minutes, so I want to wind things down. But thank you so much for listening to my presentation. I enjoyed this project, and it was a great semester, so thanks everyone. Bye.